the engineer. Energy loss in a waveguide. The waveguide loss is a loss of energy due to a micro and macro bending, uneven distribution of the refractive index at the core jacket interface, or the variations in diameter or interface shape. Waveguide attenuation. People also ask, what are the losses in waveguide? What are two types of losses in waveguides? How do you calculate waveguide attenuation? What are the properties of a waveguide? From physics.libretext.org, 12.4 energy losses in the waveguide walls. Physics, June 21st, 2021. Energy losses in the waveguide wall. These losses are due to the component hertz. Hertz is a frequency. They are synonyms whose amplitude at the walls ... Energy loss in a waveguide. Waveguides and resonant cavities. Energy loss. By resonant cavities, what they're speaking to are things that have some amazing names that came out of the 1950s, 40s, 30s even, up into the 60s and 70s. These are amplifier tubes called things like klystrons, reflex klystrons, magnetrons, phantostrons. You could Google, what are the names for resonant cavities? These are radar things. These are high energy transmission things. These are very high frequency things. This is the electricity that doesn't ride in the wire, it rides on the wire. And that question, energy loss in a waveguide, is very relevant to understanding radar principles, radar design, and radar measurements. What you expect to see at what point in time of that wave's travel. From the klystron, as example. I believe klystrons are what's in microwaves. 2.1 gigahertz resonant cavities, I believe, but the memory's tiring. So this waveguide thing, this high frequency energy thing, all these questions were pretty well answered in 1970s for some people that had the privilege of getting to some very specific schools within the military, or on a civilian corporate side, some very specific design and engineering for radar systems, as example. From mechanical engineers trying to figure out how fast that radar should spin, how fast can they make it spin, to electronic engineers figuring out the waveforms coming back from that massive blast of energy sent out into the sky. Enough energy that it can be sent over the horizon, reflected off of the layers of atmosphere. And something on the other side, unseen, could reflect back enough signal, enough energy to say, hey, I'm here. That's radar. It's amazing. Amazing. Came out of late World War II. The first components for it basically came from England and some top secret research they were doing. That little thing, that klystron, that magnetron, that phanostron, whatever name, nomenclature being used, depended very much on the corporation. This is Raytheon, this is Hughes, this is a number of other. There are dozens of high-end electronics design outfits and companies. And then you marry them with chip manufacturers now. My world started as analog world, tubes, capacitors, and then a few transistors here and there. Tubes, lots of tubes, low voltage tubes, high voltage tubes. So, there you go. Energy loss in a waveguide. End of presentation. But this is the well-known physics of high frequency energy. This could be related to the Havana syndrome I've mentioned before. This could be related to a microwave engineer that has to climb a tower to do a service for something maybe unrelated, that has to de-energize that tower, or has to know the rules for going up the tower. So, see how this goes. Peace out, neighbors.